Generators used for wind energy conversion. Coming to the different generators used for wind energy conversion. For wind power generation, normally the following generators are used. One is the squirrel cage induction generators in single output mode. Second, wound rotor induction generators in double output mode. That's known as doubly fed induction generators, DFIG. Common it's known as DFIG. Here only one out, but here two outputs. The third one is called synchronous generators, that is one field and permanent magnet. Induction generators are the most commonly used generators in wind turbine, and synchronous generators that runs at a fixed speed, but induction generators run at variable speed. That's called it is an asynchronous generators. Now we are going to concentrate this squirrel cage induction generator as well as doubly fed induction generator that are widely using for the wind energy conversion. Now let us see the basic principle of induction generator. In order to explain that one, let us first see the torque speed characteristics of induction machine. So this is the torque speed characteristics. Torque is on y-axis, speed is on x-axis, and this is here at the synchronous speed. This corresponds to the synchronous speed ns, and if speed is less than the synchronous speed, that is working as an induction motor, and if the speed of the machine is more than the synchronous speed, it is working as a synchronous generator. Therefore, this region corresponding to induction generator operation, and this region is induction motor operation. Now here, if an induction motor is driven at a speed greater than the synchronous speed by an external prime mover, the direction of its induced torque will be reversed and it will act as a generator. That is, if it is run at a speed more than the synchronous speed by a separate external prime mover, that will be working as an induction generator. Therefore, this region corresponds to induction generator region, in which the speed of the rotor is more than the synchronous speed ns. And as shown in the figure, the torque speed characteristics, that is, there is a maximum possible induced torque in the generator mode. That is the maximum value of the torque. That is this is the maximum torque possible one. That is a maximum possible induced torque in the generator torque. This torque is what known as pushover torque. The pushover torque is the maximum torque in the generator mode of induction generator. This is the pushover torque. And since it lacks in this, unlike the synchronous machine, it does not have any separate field winding. In induction machine, there is no separate field winding. Therefore, an induction generator cannot produce reactive power. Since there is no separate field winding like synchronous machine, we have to provide separate mechanism to meet the reactive power requirement. Therefore, in this induction generator, that cannot produce the reactive power. Another point is that an external source of reactive power must be connected. The same thing following to this one, connected to it at all times to maintain the stator magnetic field. That is required in the case of course, the induction machine. For this is corresponding to induction generator operation. Continuing the basic principle of course induction machine, it's called induction generator. That is, if the speed of the rotor is more than the synchronous speed, that is working as a generator. And the one great advantage of an induction generator is its simplicity. It is very simple in construction, and induction generator does not need separate field circuit and does not have to be driven continuously at a fixed speed, unlike synchronous generator. That's another point to be noted for a advantage of the induction generator. For the speed of that induction generator will be variable, unlike synchronous generator. As long as the machine speed is some value greater than the synchronous speed for the power system to which it is connected, it will function as a generator. If the speed of the rotor is more than the synchronous speed, normally the synchronous speed is given by ns equal to 120 f by p. That's a standard equation, is the synchronous speed ns equal to 120 into f divided by p. F is the frequency and p is the number of poles. That is called a synchronous speed. If the rotor is made to drive or to rotate more than the synchronous speed, that will be working as induction generator. That will be working as an induction generator. Therefore, as long as the machine speed is some value greater than the synchronous speed for the power system to which it is being connected, it will function as a generator. Therefore, this region is the induction generator operation region. This is the speed and this is the torque. Of course, torque is negative here. You can say that this is the pullover torque is the maximum torque, negative torque, and this is a region which is working as a induction generator. Now let us see doubly fed induction generator. Normally it is known as DFIG, doubly fed induction generator. Doubly fed induction generator consists of wound rotor induction generator, WRIG, wound rotor induction generator. Also it is called as a slip ring induction generator. Both are same, wound rotor induction generator or slip ring induction generator, in which the rotor, here you can say that one, that consists of, this is the rotor and this is the stator. This is the rotor of the induction machine and this outer one is called the stator. And stator windings are directly connected to a three-phase grid. Therefore, the stator winding, can say that is directly connected to the grid. Of course, through a three-phase transformer is there, that is directly connected to the grid, and connected to a three-phase grid, that this one. And the rotor windings are connected to the grid through a bidirectional back-to-back voltage source converter. That is, this is the rotor is connected to the grid. This is also grid, and through a back-to-back connected voltage source converter. The same thing that is shown here. The same diagram, same thing is shown here. In that one, see, let us see that one. This is the wind turbine, and the wind turbine, of course, that is connected to the rotor through a gearbox mechanism to change the speed or to increase the speed. That is, this is coming the rotor of the induction generator, and this is stator, and the stator is directly connected to the grid. So of course, through a three-phase transformer is there, and from the rotor, that is, this is the inside one, this is the rotor, and the rotor will be inducing a voltage that depends upon the difference in rotor speed and synchronous speed. That's called the slip of that one. Slip, it is called the difference of synchronous speed and the rotor speed, we call it as slip. And there will be a voltage inducing here on the rotor side, which is having a that, of course, the slip frequency, or it is a variable voltage, variable frequency available at the rotor side. Therefore, but here side you have a fixed voltage and fixed frequency on the grid side. Therefore, in order to connect a variable voltage, variable frequency into a fixed frequency, fixed voltage, there should be, that's called the frequency converter. The same frequency converter is this one. This is indicating a frequency converter, in which the first one is called, this is the, of course, the that converts the variable voltage, variable frequency signal into DC, or that is called, it is a rectifier. The operation is a rectification. In this case, if that converter, we call it as rotor side converter, RSC, that is controlled by this one. Therefore, here you will be getting a DC voltage. Of course, there is a change the DC voltage. There is a chopper mechanism, is a DC to DC converter, and again that DC voltage is to be converted into an AC voltage that can be connected to the grid. For that DC to AC converter, we call it as, normally it is called inverter, and that converter we call it as grid side converter, GSC. Therefore, that controller is here. Therefore, this is a grid side converter controller. This is the rotor side converter controller. Anyway, here you are getting the output frequency of this grid side converter is same as the grid frequency and as well as the grid voltage. Therefore, this is the schematic connection diagram of a doubly fed induction generator, in which there are, why it is called doubly means that rotor is connected to the grid through this mechanism, and stator is directly connected to the grid. Therefore, both sides are connected to the grid. That's called doubly fed induction generator. So it's called doubly fed induction generator. The name doubly fed is referred to the fact that the voltage on the stator is applied from the grid and voltage on the rotor is induced by the power converters. That is, the voltage doubly fed is referred to the fact that the voltage, this is a stator. Outside this is a stator that is directly taken from the grid, is connected to the grid, and the rotor that is inside that one, that is from, it is connected through the converter. Through the converter it is connected. For the voltage on the rotor is induced by the power converter. This is called the power converters that controls the power flow from the rotor and the grid. Therefore, that consists of two converters. One we call it as a rotor side converter RSC, and second one we call grid side converter GSC, that are controlled separately. And of course, there is a chopper which is to control the DC voltage. That this is called a DC voltage, DC bus having a capacitor is there, and that voltage can be controlled by the chopper. Therefore, DFIG can operate at variable speeds. Different speed it can operate. Therefore, this is a schematic diagram of a doubly fed induction generator. Continuing the same doubly fed induction generator, here same diagram, but I already explained in the previous slide. Same thing only. Here we can see that one, this part, that is that consists of RSC and GSC, and this part that can, of course, the DC bus also, that is same like this one only. Here this is a that is built by a power electronics. Switches are there, the IGBTs are there. In each leg there are two IGBTs. Leg, there's a three phase, actually this is the voltage is three phase. In each there are three legs are there. In each leg there are two switches. That is that switching action is done by using the IGBT, insulated gate bipolar junction transistor by IGBT. Therefore, this is the rotor side converter, and this is the grid side converter, and to this one, this is connected to the rotor and this is connected to the grid. For this is the DC bus, that to make it test voltage we are connecting a capacitor here. Therefore, this is what this one, this is same, this one is the circuit is this one. Therefore, the crowbar will short circuit, that is this one, this crowbar, that is as a protection only is given. The crowbar will short circuit the rotor windings through a small resistance when excessive currents or voltages are detected. That's just like a protection is provided that. Therefore, this is the doubly fed induction generator, and this is the different converters, RSC as well as GSC, rotor side converter and grid side converters. Now, continuing the doubly fed induction generator DFIG, there are, as I already explained, there are two power converters. One on the grid side, that is, this is on grid side, and another one is on rotor or rotor side, RSC as well as GSC. Both can be controlled independently. That is, the controlling mechanism is that both the grid side controller and the rotor side controller that can be controlled independently. The function of the rotor side converter is to control the generator in terms of active and reactive power by ensuring minimum power loss during the power conversion. Minimum power loss, to ensure the minimum power loss, we can control this RSC in order to have the in terms of the required active and reactive power. Basically, RSC is that is rotor side converter. The function of the RSC converter that converts the slip frequency voltage. For the rotor is running less than the synchronous speed. Of course, not less than as such. In induction generator mode, it is more than. Actually, it's more than. In induction generator, the rotor frequency will be more than the synchronous speed. So then only it will working as an induction generator. There will be a speed depending upon the difference in synchronous speed and the rotor speed. That's called a slip. And depending upon that one, there will be a voltage induced on the rotor, and that voltage is converted into DC by RSC. Therefore, the RSC converts the rotor slide slip frequency voltage into DC voltage, or in the reverse case also, the DC voltage can be converted into a variable frequency signal. That is, it is a bidirectional one that can be done by RSC, that is rotor side converter. Therefore, GSC, that is grid side controller, or that controls the DC voltage, that the DC link voltage, that is the DC link voltage also converts the DC voltage into an AC voltage by this grid side converter. Or if DC voltage is converted to AC voltage, this is called an inverter. Now, that is during the over synchronous situation, that is if the rotor speed is more than the synchronous speed, if the rotor is running more than the synchronous speed ns, which is equal to 120 f by p, it's called over synchronous speed. In that case, the is more than the synchronous speed, power, then the power is fed from the rotor into grid. In that case, the power will be fed from the rotor into the grid. Therefore, in that case, this is working as a rectifier, or this variable voltage, variable frequency rotor voltage, that is converted into DC, and that DC is again converted into AC by an inverter that is fed to the grid. So the power flow will be in this direction if the rotor speed is more than synchronous speed. And during over synchronous speed, the rotor speed is more than the synchronous speed. The power is fed from the rotor into the grid. And during the subsynchronous speed, that is, if the rotor speed is less than the synchronous speed, that is, during subsynchronous speed, the power flow will be different. That power flow will be from the grid side into the rotor side. In that case, this is working as a rectifier, and this is working as a inverter. Therefore, since these both are bidirectional one, power flow can be, if it is over synchronous speed, the power flow will be in this direction. If subsynchronous speed, the power flow will be in the opposite direction. Therefore, and during the subsynchronous situation, that is rotor speed is less than the synchronous speed, the power flow is from the grid into the rotor. That is using the bidirectional converters. Both are bidirectional converters. The power flow can be either in this direction. That is when during the super synchronous case speed, and subsynchronous case, the power flow will be in the opposite direction. Therefore, that power is taken from the grid into the rotor, or from the rotor it is going to the grid. That is the one thing. Second, from the stator it is directly connected to the grid. That is why it is called doubly fed induction generator. Therefore, this is the wind turbine that is connected to the rotor, and through a gearing mechanism is that changes the speed of, because the rotor is rotate this, the wind turbine is rotating so slowly, but you have to increase the speed. That is done by the gearing mechanism, that is so that the rotor speed will be increases. If the rotor speed is more than the synchronous speed, that is working as a induction. Of course, it's a generator. It's working as a generator. Now, continuing the doubly fed induction generator DFIG, in both condition of over synchronous and subsynchronous case, energy is fed from the stator into the grid. That is always, even either super synchronous or subsynchronous case, the energy from the stator is injected into the grid. Both cases, energy is fed from the stator into the grid. Normally, the grid side converter operates at unity power factor. The crowbar will short circuit the rotor windings through a small resistance when excessive currents or voltages are detected. Therefore, this is provided for a protection purpose. Therefore, the doubly fed induction generator machine is a wound rotor doubly fed electric machine and has a several advantage over conventional induction machine in wind power application. The doubly fed induction generators are widely using in wind power extraction. Continuing the doubly fed induction generator, advantages of doubly fed induction generator, same diagram that I already explained. The primary advantage of doubly fed induction generator DFIG when used in wind turbine is that they allow the amplitude and frequency of the output voltage to be maintained at a constant value no matter the speed of the wind blowing on the wind turbine rotor. That is, even though wind speed is changing, you will be getting a constant voltage and constant frequency output. That's the advantage. And DFIG is able to control the reactive power, and thus the power factor can be improved by using these converters. The power factor can be the two converters, RSC and GS and grid side converter GSC. The power factor can be improved, and it is also possible to decouple the active and reactive power controlled by independent control of rotor excitation. By independently controlling the rotor excitation, we can have the active and reactive power control. Then the limitation is that since it is a slip rings are required in the wound rotor induction generator. The slip rings are required. Therefore, it is a need of slip ring as well as converter cost. These are the some limitation of this doubly fed induction generator, and it is very sensitive to the grid faults. Therefore, these are two limitations of doubly fed induction generator, but there are a lot of advantages. That is why these are widely used in the wind energy extraction. Now the second one, but we have to see the induction generator is the squirrel cage induction generator, SCIG, squirrel cage induction generator. That is shown here, the different parts of the squirrel cage induction generator is shown. This is the stator and this is the rotor. The rotor bars are the end rings are the. So this consists of rotors and this consists of the stator of a squirrel cage induction generator. A rotor is made up of a cylindrical core, that is this one, cylindrical core with copper or aluminum bars short circuit at both ends by end rings. Therefore, the end rings are there, that will be shorting the rotor bars. And stator contains the winding that are connected to the grid. Therefore, the stator three-phase winding is that are connected to the grid. Therefore, this is squirrel cage induction generator operates based on the electromagnetic induction when a rotor is directly excited, but when here the rotor is not directly excited, unlike the synchronous machine. It's not directly excited, but induced from the magnetic field produced by the stator. For when this is directly connected to the grid, that will be inducing a magnetic flux, and due to that one, that is a rotor is rotated. That is, since that cutting that magnetic flux, a voltage will be inducing that will be driving a current through the rotor bars. Therefore, squirrel cage induction generator operates based on the electromagnetic induction where rotor is not directly excited but induced from the magnetic field by stator. As wind rotates the wind turbine, the mechanical energy is transferred to the squirrel cage induction generator rotor causing to rotate. And this rotation induces a current in the rotor bars. And due to the rotation, that will be inducing a current in the rotor bars. Continuing the squirrel cage induction generators, it's connected to the grid connected mode, in which fixed speed wind turbine system, a system with a squirrel cage induction generator coupled to a turbine through a gearbox. Therefore, it's a fixed speed wind turbine system with a squirrel cage induction generator coupled to a turbine through a gearbox. The gearbox steps up the rotor speed to a value matching a 50 or 60 hertz utility. Therefore, that is connected to the grid. That speed change is done by the gearbox mechanism. The network, that is the RPM will be corresponding to that the required output. To generate 50 hertz, the required RPM is 1500. To generate 60 hertz, 1800, like that one. Therefore, for a 4-pole machine, that is the speed required to generate 50 or 60 hertz signal. Therefore, this gearbox and nozzle box can be used to convert the rotor speed to the required speed so that the generator output can be connected to the grid directly. It can be directly connected to the grid because grid will be, if it is a 50 hertz grid, the supply frequency is 50 hertz, then this is to be run at a speed corresponding to 1500. That is, soft starter is a solid state device. That is, soft starter is a solid state device that protects the AC electric motor from damage caused by the sudden influxes of the power by limiting the large initial inrush current associated with the motor startup. That's a soft start mechanism is there. And of course, here there is a capacitor is required to meet the reactive power requirement. That's a capacitor is also required. Therefore, this stator is connected to the grid. Of course, capacitor to supply the reactive power is there, and this is rotor is connected from the turbine through a gearbox mechanism. Continuation of the squirrel cage induction generator. In of course, wind energy conversion systems, squirrel cage induction generators are used in conjunction with a gearbox to match the turbine mechanical speed to the generators required to operating speed. That is, required by a gearbox mechanism is used, and the gearbox that steps up the slow rotation of the turbine to higher speed required by the squirrel cage induction generator. That is done by the gearbox method or that system. For the generator output at any frequency and voltage can be converted into grid compatible voltage and frequency using power electronic converters and inverters. That is shown here. Therefore, this is a squirrel cage induction generator. Advantages of squirrel cage induction generator used in wind power plant. Advantage is that better wind energy utilization is that reduces reactive power demand on the self-excited capacitor bank. Very simple in construction, robust size, rugged construction, relatively cost is less. A rectifier can generate excitation current for the generator, fast transient response, few parts or so reliable operation. That is for a squirrel cage induction generator used for the wind energy conversion. Disadvantages of squirrel cage induction generator that is used in wind power plant: noisy operation and has very low efficiency. Additional components such as reactive power compensator is required in the circuit. For smooth grid connection, a soft starter is required. Gearbox maintenance is frequent, so cost increases. So these are some disadvantages of squirrel cage induction generator that are used in wind power plant.